let's talk about some things to watch out for when you're looking at the graph of an equation. So here we see the first equation we were looking at in the previous video. This is the graph of 2x minus y squared equals 4. And one thing I notice about this graph is that it is symmetrical. That is, the x-axis runs right through the middle of this graph, cutting it into two identical halves. So the part above the x-axis and the part below the x-axis are mirror images of one another. So we would say that this is symmetric with respect to the x-axis. So for every point on the graph above the x-axis, there's a corresponding point down below the x-axis, and vice versa. We saw that 4, -2 was one of the pairs of numbers that satisfied the equation, so that point is on the graph. But 4, +2 is also on the graph. We saw that the point 6.53 is on the graph. But down here, the point 6.5, -3 is also on the graph. So for every point on the graph of this equation, you've also got a point with that exact same x-coordinate, but the opposite y-coordinate. The negative or opposite of the original y-coordinate, you have a point that's also on the graph. So we could have guessed that that was going to happen by looking at the way the equation was set up, because the y-coordinate in the equation is being squared. So if y is a negative number, or if we replace y with -y, then when we square that, a negative times a negative comes out the same as a positive times a positive. So if you replace y with -y, and then the equation tells you to square that, well, -y times -y is, a negative times a negative is positive, y squared. So it's equivalent to the equation we started out with. So that's one way to test for this kind of symmetry. From the equation, if you replace y with -y and then simplify, it reduces to the same as the equation you started with. So that's one of 3 kinds of symmetry that we can watch out for. The one we just saw was the one I've got in the middle here, symmetry with respect to the x-axis. So that's where the top half and the bottom half are mirror images of one another on either side of the x-axis that runs right through the middle of the graph. So graphically, that means that whenever a point xy is on the graph, x-y is also on the graph. The point with the same x-coordinate, but the opposite y-coordinate. And algebraically, when you're working with the equation itself, that means that replacing y with -y in the equation gives you an equivalent equation. It simplifies down to the same equation you started with. Symmetry with respect to the y-axis would be something like this, where the y-axis runs right through the middle of the graph, and then the left half and the right half are mirror images of one another. So in that case, when you look at the graph, whenever a point xy is on the graph, -xy is also on the graph. That would be a point with the same y, but the opposite x. And then you can test that in the equation by replacing x with -x and seeing if it simplifies down to the same thing you started with. And there's also what's called symmetry with respect to the origin. So this time the origin, the point 0, 0, is kind of right in the middle of the graph. And if you start that and go off one way, like into quadrant 1, and then you go the other way down into quadrant 3, you get sort of the same thing happening, just the opposite. So if it's symmetric with respect to the origin, you could take the whole thing and just rotate it through 180 degrees, and it would match up with what you started with. So whenever a point xy is on the graph, negative x, negative y is also on the graph. Like if you have the point 1, 1, you also have the point negative 1, negative 1, where you've taken the opposite of both the x and the y at the same time. So in the equation, if you replace both x with negative x and y with negative y at the same time, then you can simplify it down to where it was equivalent to what you started with. Another thing to watch out for when you're looking at equations, look at this equation. We were working with this as an example in the previous video, but notice that there are 2 points on this graph where the graph crosses or touches or intercepts the x-axis. And we call those points x-intercepts. So this graph has an x-intercept here at the point 2, 0, and another one here at the point negative 4, 0. You can see those on the list of xy pairs, 2, 0 and negative 4, 0, and you can recognize those as being x-intercepts because they have 0 for their y coordinates. So an x-intercept is going to always be on the x-axis, and it's always going to have 0 for its y coordinate. So if we were just looking at the equation and we didn't have a graph to look at, we could say, okay, if x is 0, or sorry, if y is 0, what can x be? Now that would involve solving an equation, in this case a quadratic equation, which hopefully you've seen before, but we haven't talked about yet in this class. We will get to that. And then the y-intercept is a point where a graph touches or crosses or intercepts the y-axis. So in this graph, that happens down here at the point 0, negative 8. So for the y-intercept, the x-coordinate is 0. So in this equation, the point where x is 0, y is negative 8. So if you're looking for the intercepts, the x-intercepts or the y-intercepts or both, on a graph, you're looking at points where the graph crosses or touches the x and y axes. And if you're looking at the actual coordinates, the pairs of numbers, x-intercepts have 0 for their y coordinate, and y-intercepts have 0 for their x coordinate. So a y-intercept is a point where the graph touches the y-axis, its x-coordinate is 0, and you can find it from the equation by plugging 0 in for x and solving for y. An x-intercept is a point where the graph touches the x-axis. The y-coordinate is 0, so from the equation, you can plug in 0 for y and solve for x to find x-intercepts. So now let's look at some examples of equations and their graphs. Here we're looking at the equation x plus y equals 5. Here's a list of some of the pairs of numbers that work in that equation. In each case, the x and the y together add up to 5. So you can have negative 2 plus 7. You can have 1 plus 4. You can have 5 plus 0. You can have 9 plus negative 4. But for all of these pairs of numbers, the x plus the y equals 5. And here's the pattern they fall into. Here's the graph of that equation. It's this straight line here that includes all those points 5, 0, and 1, 4, and negative 2, 7, and 9, negative 4, and all those others. And does this graph have any of those three kinds of symmetry we talked about? Is it symmetric with respect to the x-axis, or the y-axis, or the origin? No, none of those. Does it have x and y intercepts? And if so, what are they? Well, the y-intercept would be this point where we cross the y-axis, and that would be the point 0, 5. The x-intercept would be the point where we cross the x-axis, and that would be the point 5, 0. Notice for the y-intercept, the x is 0. So if you told me the y-intercept was just 5, that'd be okay, because I know you mean, okay, that's the point where y is 5, and we don't even need to say that x is 0, because if we're on the y-axis, x must be 0. And the x-intercept, well, that happens right here where the x-coordinate is 5, and since we are on the x-axis, the y-coordinate must be 0. Let's look at another equation. This one has y equal to 2x plus 1. So every point on this line, whatever the x-coordinate is, if you take 2 times that number plus 1, that'll give you the y-coordinate that goes with it. Does it have any of those 3 kinds of symmetry? Nope. What about intercepts? Can you see the y-intercept? That's right here at 0, 1. The point where y is 1 is the point where this line crosses the y-axis. And what about the x-intercept? Well, it's right here. I can see it on the graph. And it looks like it's about halfway between -1 and 0. It's not on this list here. There isn't a point on the list that has a y-coordinate of 0, but this is not a complete list. So if we wanted to figure out exactly where that is, we could go to the equation. We could put 0 in for x, or sorry, I'm sorry, I had that backwards. We put 0 in for y if we're looking for an x-coordinate. And then solving this equation, we can subtract 1 from both sides, divide both sides by 2. We get x equals -1/2. So yeah, that's where that is. The x-intercept is the point -1/2, 0. How about another one? Y equals x squared minus 1. Does it have any of those kinds of symmetry? Well, this time this is symmetric with respect to the y-axis. Notice how the y-axis runs right through the middle of the graph, cutting it into 2 equal halves. Notice how when you look at the table of values, you've got when x is 3, y is 8. When x is -3, y is 8. 2, 3, -2, 3. 1, 0, -1, 0. The x in the equation is squared, so if we replace positive x with negative x, that gets squared. It's equivalent to just y equals x squared minus 1. Y-intercept, 0, -1. X-intercepts, well, there's one here at -1, 0, and there's one here at +1, 0. I'm going to come back in the next video and we'll look at a few more examples, including some more interesting graphs.